Example 3 is talking about the Gateway Arch in St. Louis. It's 630 feet tall from its base, which is 630 feet wide. It can be roughly modeled by a parabola. What is the average height of the arch above the ground? And so if I didn't account for the fact that some heights are used more than once or for a longer period, I could just try to average them. 630 divided by 2, 315. And so we're going to find out if it is 315 or if it's not, and then we'll talk about why. So 315 is, let's say there-ish. But since I have more points closer together up here, I think the height is going to be skewed a little higher. And let's use the average value formula to discuss that. Okay, so the first thing we need to talk about is the interval. And so this is going to be from negative 315 here to 315. And so I could look at a looking for average height right here. So h bar equals 1 over b minus a. So 1 over 315 minus negative 315 times the integral from negative 315 to 315 of our function. And so the function is 630 times 1 minus x over 315 squared dx. Okay, now we're going to modify that to make it nicer to deal with. The first modification that we're actually going to do is because this function right here is even, we're going to double the bounds and replace that bottom bound with 0. So that's the first thing that we're going to do. So we'll rewrite this as, I'm going to combine the denominator. 315 plus 315 is 630. I'm going to multiply by 2 and then change my bounds to 0 to 315. And then this 630 we're going to take out here over this 630. They're going to cancel. So I'm also moving that one out just to get my coefficients all together, and because they cancel, I don't want to have extra 630s just floating around. And then now we have the 1 minus x squared over 315 squared dx. Okay, so I hope that looks good. And then we can reduce the 630s, and we're just going to do twice the integral from 0 to 15 of this function. Okay, so that should be, we're going to integrate now. So 2 times, when I integrate 1, I get x. X squared over 315 squared, that's a coefficient. So I can think about this as 1 over 315 squared times x squared. And when I integrate x squared, I get x to the third over 3. And then between our bounds between 0 and 315. Okay, so we have 2 times 315 minus 315 cubed over 3 times 315 squared. And then we have minus 2 times 0 minus 0. So that piece goes to 0, which is one of the reasons we like to use that property of even functions, is not having to worry about plugging in a different value right there. They'll sometimes zero out. Don't always zero out when you plug in 0, but they usually make it simpler to plug in. Okay, so this is 2 times 315 minus, that's going to reduce to 315 over 3. And I can use a calculator just to finish simplifying those so I don't have to multiply 315 by 3 in my head. So we've got 2 times 315 minus 315 thirds. And so that gives me 420. All right, so back to our diagram for a second. We had noted that there were more points up high. As they're getting closer and closer, those y values are realized more frequently up high than they were below. So even though if I just take 630 and divide it by 2, I get 315, the average height that we have is 420, so it's really up here. So that's the average height, is up here at 420. It's much higher, like we expected it to be, than just the average of the straight up y values, because these are realized less, these are realized more. And so that's something that's going to be important to the architects so that they can figure out the types of material and the load that these are going to have to bear. Okay, so definitely something that needs to be considered in terms of making the object. All right, let's take a look at the next page. This one we have a company's profits in millions of dollars, and we want to find the company's average profits. Ooh, and we get to do this one on our calculator or on Desmos, so I don't have to integrate it by hand, but we will set it up. So we're looking between 0 and 12 months. So our average profits, P bar, are going to be 1 over 12 minus 0 times the integral from 0 to 12 of our P of x function. So our 25 x to the negative 1 times sine of 4x plus 100 dx. And we're going to add in an extra set of parentheses right here before we start typing it in Desmos. Okay, so on Desmos, we can evaluate, oops, I made it a little, that's probably the wrong window for Desmos, hold on. Ah, there's my smaller one. Okay, so there's my Desmos window. And so let's begin typing this in. We want to do 1 over 12 times the integral, int, from 0 to 12, parentheses. Then we have 25x to the negative 1 times the sine of 4x plus 100 dx. Okay, so this gives us an average value of 103.3. I'll round it there because of those 0 zeros. And so since this is in millions of dollars, we would put back on there $1 million for our units. The average profit was $103.3 million during the year. Okay, because it does mention calculator instead of just Desmos, I'll show that you can do this in your calculator if you want. And so on a calculator, I would go to math, go up, so I get to the bottom of the list for that fint, function integration, I'll type in the bounds. So before this, actually, I'm going to insert that 1 over 12, and then we have the bounds 0 to 12, and then we have our 25 x to the negative 1 times the sine. I think I'm actually going to have to change my mode to make sure I'm in radians, because I was working with, oh, I'm in radians, good. Just want to make sure. I was working with pre-calc on this calculator earlier, and it might have been in degrees. And then of 4x, and then go back here, add my 100, and finally the dx. And I get, ooh, it's thinking really hard. It takes it a while, this poor little device. But hopefully it's going to come out with 103.3, just like Desmos. So you can do things like this in the calculator as well, if you have the patience to sit there and wait for it to load. In this next example, we're going to take a look at the velocity of blood flow at a distance along the central axis from some artery of fixed radius r, given by V of r equals k times r squared minus little r squared, where k is a positive constant and little r is between capital R and 0. Popsicle time, hold on. So our goal is to find average velocity, and so we're going to integrate the velocity function over this region. So average velocity is going to be 1 over r minus 0 times the integral from 0 to r of the velocity function. So in the velocity function, little r is the variable, capital R is fixed, and k is a constant. So these are both constants actually. Little r is the only variable. So we have k r squared minus little r dr. Shh, hold on. Now because k is a constant, it's going to make sense for me to pull it out over this. So I'm going to have this written as k over capital R times the integral from 0 to capital R of our capital R squared minus little r squared dr. That cleans it up a little bit, because this isn't a true product. That's really a constant. Constants can be pulled out just like numbers can. It is a number. I just don't know what the number it is. And then we integrate this. So we have k over capital R times, now r squared, capital R squared, is a constant in terms of little r. So if I integrate 4, I'd integrate it into 4r. So capital R squared integrates into capital R squared little r. Little r is the variable, so it's going to use the power rule, and we'll get 4r cubed minus 3. And then we're evaluating that between 0 and capital R. Now we're going to evaluate. So we have our k over capital R, and then we have capital R squared times capital R minus capital R cubed over 3 minus k over capital R, and then we have 0 minus 0 over 3, and so that's all just going to be 0 on that side because that's what I get when I plug 0 in. And so this simplifies to k over capital R times, this is r cubed minus r cubed over 3, so it's going to be 2/3 r cubed. And then when you reduce one of these r's with one of those r's, you're going to end up with 2/3, and you'll have k capital R squared. So the average velocity is this formula. It's 2/3 times k times r squared. So it's going to be found by knowing the fixed radius of the artery and the constant, which is something to do with how far away you are from the central axis. And that's how you can find the average velocity of that blood flow.